talk for today is actually adapted from a presentation that I gave a few weeks back at the AAA SciTech conference. And then I modified things and added more detail to it, because in the conference I had only 10 minutes, so everything was rushed. But here we can actually go in detail and discuss things more properly. So first, I'd like to acknowledge the support of the Air Force Office of Scientific Research and the Australian Research Council in giving us funding to conduct the research. And as I said, there is a paper on this work, which was very recently published. Here's the DOI link and also a QR code if you guys want to check it out. All right, so let's look at the background of the research and why it matters for our whole scientific community. So first, I'd like to say that the work that I'm currently doing in hypersonic air elasticity is important because of one main thing. First, in aeronautics in general, we want to design things that are light. And that's because of the weight constraint in the whole aircraft design process. But then when we start to design light things, we inherently lead to the construction of compliant structures. And what do we mean by compliant? Compliant is a fancy word that we use for flexible structures as well, and which basically means that it's structures that deflect as it interacts with an airflow, and that can lead to certain problems if not taken care properly. So there's different types of structures that we can analyze, but I'd like to focus this research for a particular boundary condition set, which is called the clamp-free. There's great studies from UNSW Canberra actually on cantilevered panels, so clamped free. There is also a lot of studies on fully clamped panels, which are representative of skin panels in aircraft fuselage. But I think it's important for us to understand that at a fundamental scale, so that we can move on to more realistic structures without losing accuracy in our air elastic prediction tools. So right now, clamp-free. This is the direction of the flow. So flow hitting the clamped edge and being parallel to the free edges. And regarding that particular structure, there's 3 air elastic excitation sources that we can identify in wind tunnel testing. So first of all, when we fire the tunnel, and by the way, it's a short duration hypersonic tunnel that I'm using for my PhD. What happens when we fire the tunnel is that it transmits to the panel a huge flow arrival impact load. And that's what we call coupling independent movement induced excitation. So that's one source of air elastic excitation, of vibration, right? The other source is the fluid structure interaction, which is developed between the structure and the fluid, which is sustained by the shockwave boundary layer interactions in this case, because we're dealing with a shock impingement situation, and I'm going to explain why I'm choosing that particular configuration. And the last air elastic excitation source that may contribute to our problem is the free stream pressure fluctuations. So that's called the extraneously induced excitation. Extraneous because it's far away from our problem. It comes from the free stream rather than the model itself. Okay, so as I said, before we dive into the fluid structure interaction aspects of this problem, the particular flow configuration that we're using is a shock impingement. And some of you may be asking, why is he doing that? If we look at hypersonic airframes moving through air, typically the forebody of the vehicle invariably leads to the formation of shock impingement in the rear parts of the airframe, and that impingement can lead to catastrophic failure, and this is why we care about that. So in this case, we have a shock generator, which is able to impinge a shock on the panel, as they're marked here. Let me see if I have a laser. I do have a laser, so here's the panel. So it impinges a shock, and then since we have a shock right here on the panel, an adverse pressure gradient is formed, and that leads to the formation of a recirculation zone, also called separation bubble. And then we have a separation and reattachment shock. So that's the very basic configuration of shock impingement case. So with that, we can establish a comparison between a range of shock impingement experiments. They were done by these people right here. Actually, some of them from UNSW Canberra. This guy here, Gaetano Curao. And in this plot, I'm basically getting the relationship between the structural compliance ratio, lambda, and the reduced frequency, so that I could understand where is my research sitting among the growing body of air elasticity experiments. So as we can see here, there's a linear trend between all these experiments. And it turns out that the very bottom case is a cantilevered, clamp-free experiment. And it's interesting to note that the majority of the fully clamped experiments is sitting in the upper right region. So the importance of my contribution is really bridging the gap between these cantilevered and fully clamped panels, trying to understand the basic fundamentals that govern the fluid structure interaction. So for that, we did experiments in this wind tunnel facility at University of Southern Queensland, our partners. And this is a Ludwig tube operated in free piston compression heated mode. And it was operated at a total pressure of 1 megapascal and with the main free stream properties indicated in the table. It's worth noting that the Reynolds number is transitional for the length scale that we are using. And we used a nozzle of Mach 6, or to be more exact, 5.8 for our studies. Here's the free stream history for the pressure, and it's pretty constant across the duration of the run, which lasts approximately 200 milliseconds, and the run-to-run variance is only 10%. So we have good repeatability with that. So regarding the experimental model, in order to capture the fluid structure interactions, we designed this following model, and I'm going to explain this better. So we have the panel illustrated in there, and the panel is bonded with epoxy to removable inserts, as shown here. And it's very interesting, actually, because beforehand, in cantilevered experiments that our research group did, we use bolts. It was like a riveted joint. But since the panel now is so thin, because we want to be able to track the panel deflections, it's so thin that we couldn't use bolts. So we ended up bonding that surface with epoxy. And we did a whole study to characterize that bonded region to mimic a perfectly bonded boundary condition. So as indicated, we have the nozzle here. And the model also consists of the model forebody and the model afterbody. It's important to note that the model forebody looks like a hammerhead configuration. Hammerhead in the sense that it has this extended area here and this extended area here. And the whole idea behind this is to delay three-dimensional edge effects on the panel. Basically, what this forebody does is delay these edge effects, and it produced a two-dimensional flow over the top of the panel. I don't want to be able to do that, right? Because when we compare experiment results to analytical predictions, we're going to be able to match them closely, and analytical predictions are 2D based, not 3D with all complications. So this is the model for body, and the model after body is formed by steam. Exactly this point here where I'm pointing, and that's basically a tensioning mechanism where we can tune the natural frequency of the panel to mimic a fully bonded clamp-free state. Moving on, we have the shock generator, which allows us to impinge a shock on the panel at different shock impingement angles, or I should say flow deflection angles, because essentially the flow is turning in itself. And basically the variations of this experiment occur with panels of different thicknesses, a thinner panel and a thicker panel, as illustrated by the H here, H meaning the thickness. And the flow deflection angle is 0 degree, 2, 5, 8, and 10. So in summary, I know we have a lot of numbers here, but in summary, we're using a rigid panel. And the reason why we're using a rigid panel is that we can have a baseline experiment and compare that to the compliant panels. And by the way, the rigid panel has tapered edges so that we can mimic the edge conditions experienced by the compliant panels. So we are comparing apples with apples. We are comparing similar things. The thickness ratio that we were dealing is these two listed here, and the flow deflection angles, as I said before, are these 5 different cases. So that's the experimental setup. And then in terms of instrumentation, our model is actually equipped with a lot of instrumentation devices, including thin film heat flux gauges, pressure transducers, the strain gauges. We are also doing pressure sensitive paint measurements of the panel to get a spatial map distribution of how the pressure is changing over the duration of the run. We also have digital image correlation from the sides of the wind tunnel. And also another instrumentation source is actually a laser profilometer, which spans through the center line of the panel. But for now, let's focus on the pressure transducer response that we obtained. So this is all the pressure transducers that we have, PT1, PT2, up to PT5, and this is a rigid panel. So basically from what we see here is that the outer dashed lines indicate the flow arrival and the flow shutdown, but the inner dashed lines indicate the portion of the run where we have a steady flow. So where the hypersonic core flow is fully established, because in this stage here, it's getting developed, but then after about 160 milliseconds, the hypersonic core flow starts to collapse. And in fact, the total temperature is expected to decrease, and we cannot properly model what's going on to the flow conditions using the isentropic relations, because we have some problems after 160 milliseconds in terms of decaying total temperature. So in order to be able to track the deflection of the panel, we created an algorithm which basically fits a Gaussian curve in the vertical direction to the intensity vector, as demonstrated here in the top right figure. And then using that, we can track the location of the panel displacement in terms of a spin-wise average displacement, because what we're really seeing here is not the center line, but rather the spin-wise average deflection of the panel. So this is what a Schillerian frame looks like, a raw Schillerian frame looks like. And here's what the deflection signals look like for these 5 points equally spaced. So this is a case where we have the thicker panel and 10 degrees. And here's just to show how the signal looks like, and then we're going to dive into that result very soon. Okay, so if you guys remember, I talked about some of the aeroelastic mechanisms that are going on. So the idea here of my work is really to decouple those effects and see whether we have fluid structure interaction or not. So in order to understand that relative significance among those different aeroelastic excitation mechanisms, we can plot some parameters that are going on with the model. First, we're getting the free stream static pressure, the time history of that value, measured as per the barrel total pressure, and then converted to free stream using isentropic relations. The signal from PT2, the pressure transducer at this location, the pressure at the center from pressure sensitive paint, and also the structural deflection from the algorithm, image tracking algorithm, which I just showed. So looking at these results, and again, for the thicker panel at a flow deflection angle of 10 degrees, we can see that the deflection, the structural deflection, it tends to shift from a structurally dominated regime to a fluid dominated regime. So what we have first resembles the response when we have a free vibration. When we do, for instance, an impact hammer test, and we have a natural decay of the response, it resembles like that. And that's expected because of the flow arrival impact load. But then as we move on through the run, we can see that that response is actually getting shifted towards a fluid dominated, which means that forcing mechanisms are present here, either due to the free stream fluctuations or the fluid structure interaction that is being developed. And we can see that via the fluctuations in the envelope of the structural deflection signal. One other thing that is important to note is that how these quantities here, the free stream pressure, the static pressure at this location, and the PSP pressure at the panel center are correlated, right? We have an increase in the first 80 milliseconds, and PT2 and the PSP pressure follow that increase very closely. But this is for a particular case, so let's look at how these results are for our experimental matrix that we tested. So here's our experimental matrix. To recall, we had a rigid panel, we had the thicker panel, and we had a thinner panel being tested at these 5 different flow deflection angles. And from these matrix here, we can observe that different structural compliance have different shock impingements. And by the way, this is a snapshot at 15 milliseconds. So we have slightly different shock impingement locations, and that actually influences the overall aeroelastic response of the panel. So let's try to understand the structural deflection. And there's a lot of information here, but I'll try to condense things as most as I can. And by the way, the full details of these structural deflection signals can be found in the paper. So let's try to understand this closely. So here's the power spectral density for the thinner panel and the thicker panel. The thinner panel being on the left and the thicker panel being on the right. And this is all the flow deflection angles that we tested. So let's try to understand step by step. So for the thinner panel, what happens is that we have lower mechanical impedance because, well, the stiffness is smaller, right? So because we have a lower mechanical impedance, the panel deflects downwards without strong resistance. And as it deflects downwards, this inherently leads to an aerodynamic stiffening effect. And then we have what we call first mode lock, where the panel is locked to oscillate predominantly in its first mode. And then what happens is that higher order modes cannot be developed because we have predominantly first mode oscillations. And then what happens is that the impact load's more slowly dissipated. Well, if we had higher order modes, we'd have higher damping, because that's nature. But then since we don't have, the impact load is more slowly dissipated, and that means that the run may actually end before the fluid structure interaction and the free stream fluctuation effects become relevant. Well, initially we have the flow arrival impact load, and then that leads to a decay, and we can actually see that in the signals in here. So I wouldn't say that these runs are useless, but turns out that we cannot really identify fluid structure interaction in here, because what's really happening is almost a free vibration. On the other hand, for the thicker panel, where we have higher mechanical impedance, we can observe that the stiffening lock-in effect is not as substantial. It's not predominant. So basically, since that stiffening effect is not as strong, the panel is more free to develop vibration in other modes. And then we can see that actually torsional modes are present. We can see here in the blue, red, and green curves, the development of torsional modes. So what happens is that since we have higher order modes now, the impact load from the flow arrival is more rapidly dissipated. And then we do have transition to a fluid dominated regime. And that's actually shown by the pure signal collected from the structural deflection in here. But that's really portrayed in the power spectrum density. And then you might be wondering, okay, so blue, red, and green are for 0, 2, and 5 degrees. So what happens at 8 and 10 degrees? So for those cases, what happens is that the panel is loaded sufficiently enough that it gets locked in the first mode. And then what happens is that high order vibration is not developed. And it turns out that the response is purely structurally dominated, because there's not enough time for that impact load to be dissipated. Okay, so I mentioned about fluid structure interaction and the coupling, but more detail is given in the paper. There is a lot of nuances that the paper addresses, comparing power spectrum densities of different signals. But let me try to summarize here for you. So what happens in the problem is that the flow arrival impact load is the dominant aeroelastic excitation mechanism, because the flow duration is so quick, right? We're talking about 200 milliseconds. Ideally, I wish we had more time so that we could analyze what's going on after that initial transient regime, but the time's so quick that turns out that the flow arrival impact itself is the dominant aeroelastic source. So it's important for us to distinguish between the relative significance between the coupling dependent movement induced excitation, the fluid structure coupling itself, and the free stream fluctuations, because they have a very similar effect. So these two mechanisms are dictated by three things, which I briefly mentioned, which is the panel thickness, which we call structural compliance, and the strength and location of the shock impingement. So the outcome of the competition between FSI and free stream fluctuation is that FSI wins for these selected runs, and the paper goes through all of them showing why it wins, whereas the free stream is more dominant than the fluid structure coupling in the other runs. So with all these results, we can narrow down the outcome of this research to two conclusions, and that's what I want you guys to take from these presentations. So first, the conclusion is that the aeroelastic response of the panel tends to shift from a structurally dominated to a fluid dominated regime. And then depending on the panel thickness, I mean, the structural compliance and the strength and location of the instant shock, the transition may or may not be completed. The second major takeaway of this study is that as we increase the flow deflection angle of the shock generator, we produce an aerodynamic stiffening effect, and that tends to lock the panel to oscillate predominantly at its first vibrational mode. And then since we don't have the occurrence of high order modes, since we are attenuating them, the structurally dominated reaction takes longer to dissipate. And then that decreases the significance of both the FSI and the free stream fluctuations. But this is a bit complex, and the nonlinear shock boundary layer induced FSI physics is portrayed in detail in the paper. Thank you for your attention, and feel free to connect with me and with us, the Hypersonic Research Group at UNSW Canberra, in the links provided.